Thanks a lot, John Marie, and thanks a lot for your patience, for staying here till the very end. I know it was a long and difficult week. So I will speak about a problem I developed with Serena and Ovidiu, and it's a problem about non-local minimal surfaces. So in a sense, this is a subject that has already emerged during a previous talk. Just recall the setting that I will use. So the main topic of this talk are non-local minimal graphs. So I will study surfaces with the graphical structure. So for me, graphical means a function from Rn to R. So my environment is Rn plus 1. So in general, if I want to look at non-local minimal surfaces, I will consider Rn plus 1 as my ambient space, and the S perimeter of the set E in the domain omega, and now omega for me in this notation is Rn plus 1, and then I will restrict to the graphical cases later on for a fractional parameter S in 0, 1 is given by the interaction. So roughly speaking, here I have to put the interaction between E and the complement of E that I denote by EC. With some component in omega. So I will have an interaction that I call LS, and here I have to put E and the complement of E, but I have to, okay, not a great use of the blackboard, but so you know that I will have 3 terms. So why do I know that I have 3 terms? Well, because E could be in omega, and the complement of E could be in omega, or E could be in omega, and the complement of E could be in the complement of omega, or E could be in the complement of omega, and the complement of E could be in omega. And here the only thing that I'm not putting is the case in which both E and the complement of E are intersected with the complement of omega, just because I consider that as an external datum. So basically, which I have in mind, for the moment at least, that omega is contained in the ambient space. Then I have some set E, and then I'm considering the interaction of points in omega, and I'm considering the interaction of points from omega to outside omega, and then I'm considering interaction points from outside omega. And I'm not considering points from outside omega to outside omega because this is for me a given datum of the problem. And of course, the interaction can be kind of general, but the simplest possibility is to consider an interaction between two disjoint sets A and B, which is just translation invariant, rotational invariant, and homogeneous, in which case one is forced to take 1 over x minus y to the n plus 1 plus s. And, and then I want to look at S-minimal sets in omega. So if omega is, for instance, a bounded set, and it's sufficiently regular to have competitors, then the next minimal set is a set that minimizes the S perimeter among all competitors which coincide with a given datum outside omega. Now, as I was saying, I'm mostly concerned here to the case of graphs. So in principle, I would like now to consider the case in which omega is a cylinder. So suppose that omega is like small omega times r, with omega in Rn minus 1. Well, the idea is that I want to look at S-minimal sets in omega. I have to be slightly careful because since omega is in this case unbounded, I have to give a special definition. In this case, for me, this actually comes from Luca's thesis. If you we say that you have an S-minimal set in a cylinder or in an unbounded domain in general, if the set is S-minimal in every bounded open sets contained in omega. And the class that I will be mostly interested is the one of S-minimal graphs. So for me, an S-minimal set which has a graphical structure, so it is, say, a subgraph of a function from Rn to R, is called an S-minimal graph. And the important thing I would say is that this definition is consistent with the geometry of the problem in the sense that if you prescribe some graph outside your cylinder omega, and then you look for the S-minimal set corresponding to this configuration, then the set is actually a graphical structure, so it is an S-minimal graph. And so if the external datum is a graph, the corresponding S-minimal set is also a graph. And so it's an S-minimal graph. And this is a result that we obtained with Serena and Ovidiu a while ago. Now, for me, one of the most interesting properties of non-local minimal surfaces is the boundary behavior. Because if you come from classical PDEs, well, boundary behavior is a difficult topic, but it works, right? So if you have an elliptic equation and you have sufficiently nice coefficients, sufficiently nice boundary, then your equation is smooth up to the boundary. Of course, pathologies may occur, but typically due to some pathologies of your domain, of your coefficients, whatever. The first surprising thing that for me was shocking when I started looking at the non-local equations was the fact that solutions of non-local equations are not smooth up to the boundary. They are only continuous or Hölder continuous. But let me maybe say something about it. Because this was for me kind of a shock at the beginning, and I didn't really understand why things go wrong. So there is this classical fact that, for instance, x plus to the s is S harmonic in 0 plus infinity. Okay. I mean, this is an example showing that if you are harmonic in even more generally, so at omega, let's say harmonic for simplicity, then U is only continuous, but not better than CS up to the boundary. So this example somehow confirms that you cannot improve the Hölder regularity at the boundary, right? And one can say, how comes? Well, one can compute. There are a number of proofs that you can do that confirms that x plus to the s is harmonic, but that's not an explanation to me. A better explanation for me is the probabilistic interpretation. So you may think that harmonicity is the analytical counterpart of the game theory interpretation that you are drifting randomly across a domain, and when you exit the domain, you get a price that is prescribed outside, right? And then the solution of the corresponding harmonic equation is the expected value that you win if you start at the point x. So in the classical case, for instance, if you take 0 value on one side, let's say, suppose that this is 1, suppose that you take a straight line here, well, the solution, if s is equal to 1, the solution is just the straight line. You say, oh, this is obvious because I know how to solve u second equal to 0 in R or in R plus, but let me give you a difficult proof of this. The difficult proof is that you take the point 1/2 and you say, well, if I start at 1/2, I have the same probability of going from one side or to the other, right? So I either get 0 or I get 1 with equal probability, which means that in the middle, starting in the middle, the expected value of victory is 1/2. Then if I start at 1/4, well, I have the same probability that I hit 0 or 1/2 where I get 1/2 as a payoff. So in average, my expected value of winning is 1/4 and so on. But now if you do the same situation in the fractional case, in the local case, well, if you start from 1/2, you have the same probability of exiting the domain on the left or from the right. But then the expected payoff is higher than 1/2, because if you exit from the left, you get 0, but if you exit from the right, you get 1 or more. So in average, so for S from 0 to 1, the expected value is actually higher. And then you can repeat in 1/4. Yes, maybe you exit on this side, or you basically go over 1/2, which means that your value is this or above. So if you take the average of these two values, well, your expected value at 1/4 has to be higher than that. And now you repeat this construction over and over. Now my picture is going to be a bit messy, right? But in principle, you take this, and you say that you are above this, and so on. So you repeat this picture over and over, and so what you get is that you have like a concave cusp-like structure on this side. Okay, so it's not a proof, but I think it's a visual justification of what is happening. Okay, so if you come from this intuition, you may say, okay, the boundary regularity of non-local objects is a little bit surprising, but continuity is always guaranteed. Now that is not true, at least for non-local minimal surfaces. So non-local minimal surfaces present boundary discontinuities. And so this is something we have discovered with Ovidio and Serena. And again, let me convince you with some pictures that this is the case. So of as minimal graphs. So this is a phenomenon that we call the stickiness. For a visual representation that you will see in a second. So again, I will try to give a heuristic pictorial motivation, then the proof is much harder, but the fact is that before trying to prove it, you have to guess that this is true, right? And coming from that kind of intuition, our first guess is that non-local minimal surfaces were regular. So how did we figure out that we were wrong? Well, because you took a simple example. So you take in 2D the case, I don't know, you can say -1 times r. So my omega here is just a vertical slab. And you take a datum outside as simple as possible. For instance, you see I like linear data outside because they are easy to draw. So let's take a linear datum outside. Okay. And then the game for us was to list all the possible suspects and to rule out the ones that are not suitable for minimization. Now, one thing that we knew is that the Euler-Lagrange equation for S minimal surfaces reads in a relatively explicit form. So if E is S minimal, then at every point is S minimal, say in omega, then for every x in the boundary of E intersect omega, the S mean curvature is equal to 0. So the characteristic function of Rn of the complement minus characteristic function of E over x minus y to the power, well, n plus 1 plus s in this notation is equal to 0. Okay, so somehow we knew that minimality implies that when I look at a boundary point and I average out the component of the set and of its complement, these components have to average off, to cancel each other. So how to complete the picture? So given this datum at infinity, so I suppose always that I'm looking at subgraphs, for instance. So the natural object that we thought was the S-minimal graph, something like this, right? Smooth and connecting the two things. But this is immediately ruled out because you can take this minimal point, and when you look at this minimal point, if you see all this yellow half plane is contained in the set, and also a little bit more, which means that when I look at the set and of the complement of the set, I have always more than half of the space. So the S minimal, the S mean curvature of this set at the minimum cannot be 0. So the simplest possible candidate is ruled out. Well, the second candidate is that, well, maybe we don't have to bend down, we have to bend up, something like this. But this is also ruled out because if I still have a global minimum, I can apply the same argument as before, and here I have much more set than the complement of the set. So this is also ruled out. So what you can guess in this way is that not only you have to bend up, but you have to bend up immediately, in a sense. So the next possible candidate is something like this. Right? And now, if you try the same trick at this point, it doesn't work because locally you see less space than half of the full space. But globally, when this line intersects these oblique slopes, then you see more set than the complement. So if I just look at this point may well have S-mean curvature 0 just because of magic compensations between close by contributions and far away. But this is still not an S-minimal graph because you can consider this point, okay? And consider now an oblique tilted half plane. So if I do this at this point, on this side I have the full set. On the other side I still have contribution from the set, so it is impossible to cancel the two contributions from this side. So this is also not an S-minimal surface. Strictly speaking, omega is an open set. So this point is not in omega. So yeah, Gianmaria is dubious about this proof. Well, if you want to do it rigorously, you have to take a line at this point and then converge. So in a sense, this already says that there is something very technical that has to be adjusted because when you want to study the boundary behavior, you want to use some kind of maximum principle at the boundary when your equation fails. So you have to distinguish the points that you can reach from inside and the points that you cannot reach from inside. That will be an important difference. Okay, but then we rule out also this. So we are out of candidates, but we have learned that the S minimal graph has to bend up, and it cannot really match the boundary in any reasonable way. So it has to match the boundary in an unreasonable way. So it has to develop a vertical jump and then bend up. If you ask me to draw the S minimal set here, I will draw something like this. And this is an acceptable candidate, at least from pictures, just because, again, if I take this as a reference point, I can get cancellations. Also, this point will get cancellations because the slope gets more and more inclined, so there is nothing that prevents cancellations to occur from different contributions. And yes, so of course this is not a proof, but it's sufficiently close to justify a strong desire to give a proof, and the proof that we gave of this fact is actually very general, and it includes a very large number of examples, and actually we proved that an arbitrarily small perturbation of the half plane, so if you just give a small perturbation of a flat half plane outside, will produce this kind of stickiness phenomenon. So for instance, if you start with a half plane, you get a half plane, but if you perturb it a little bit, then you have already a sticky surface like this. And okay, if you make it more evident, you will appreciate more the jump. But in principle, these two bumps can be arbitrarily small and arbitrarily far away. The proof of this is kind of hard, I would say, because you need to construct a barrier, and the barrier is constructed by gluing together different powers and slopes of homogeneous functions. So basically, you have some kind of linear interpolations between different powers, and you have to adapt all the parameters to make this a barrier. So that's what it is. Actually, we proved that the stickiness is a generic phenomenon. So there are cases in which you don't have stickiness, for instance, the half plane itself. But then, if you are in one of these very special cases and you give an arbitrarily small perturbation of the external datum, then what you get is a sticky S minimal graph. Also, the proof of that really relies on the distinction I was mentioning before regarding points that you can touch or not touch from inside, because to prove this kind of generic stickiness, one argument that you may want to do is, okay, let's start with something that doesn't stick. Let me try to give a picture of it. So how would you prove genericity? Well, our first attempt to prove it was like this. So suppose that you don't have stickiness, so you are in a situation like this. I don't know if it's visible or It's a while I haven't done this, so I'm a bit rusty with the water cancellation. Let's see. Okay, so wrong proof, wrong but somehow convincing proof. So let's say that you are in a magic situation in which you don't stick. And then you add two small bumps like this. And now you look at what happens, right? And we have developed the feeling that if I put the bumps up, the picture inside will also bump up. So the only thing that can go wrong is that it goes up without stickiness. So for instance, it goes up like this. But then I translate it down, I translate it up, and then I have two S-minimal graphs, and I have to be okay, this wanted to be a translation of this one. This is a translation of this one that touches. No, sorry. Yes, exactly. So this is a translation of the perturbed S-minimal surfaces that touches the original one at a point. And we know that if this is the picture, this has to happen. So this creates a contradiction with the maximum principle because I have two S-minimal surfaces that touch at a point without being equal. Okay? Wrong proof because the catch of this proof is that the contact point may actually occur at the boundary. And this is actually what you expect because the stickiness phenomenon is producing bumps basically at the boundary. So you have to refine this proof in order to allow the use of a maximum principle at the boundary with respect to the points that are reached from inside. This is a little bit tricky and requires, so making this proof work basically requires a boundary analysis that we call dichotomy. So we have an alternative between discontinuity and smoothness at boundary points. Basically, for S-minimal surfaces, what it happens is that you have that boundary continuity implies boundary differentiability. This, of course, is wrong for standard functions, but it's exactly what happens for S-minimal surfaces, for S-minimal graphs. So the dichotomy, the alternative, is that either the S-minimal graph are C1 alpha up to the boundary, so they cross the boundary in a C1 alpha way, or they are discontinuous. Vice versa, if they are continuous, they are automatically differentiable and C1 alpha. And you may also consider it as a butterfly effect in the sense that the boundary derivative of an S-minimal graph can change instantaneously from 0 to infinity by an arbitrary small perturbation. Because if you put the various results together, you may say, okay, let me start with a configuration in which I don't have stickiness. And let me normalize this configuration so that the derivative is, say, 0, just because I put a horizontal slope, say, at the origin. But then I know that an arbitrarily small perturbation will produce stickiness. So not only I have a discontinuity, but what I can also prove is that the derivative at this discontinuity is infinite. So whatever you want to pose the situation, you have a butterfly effect for the derivative, which switches instantaneously and generically from 0 to infinity. Yes, one difficulty that we had in selling our papers is that they were mostly done with pictures. So there was really, again, a dichotomy, either picture or horrible calculations. And of course, not many people liked that. The fact is that the pictures were drawn by hand. So don't believe me too much when I draw a picture. It's just the intuition of the thing. Then the theorem was rigorous and quantitative. So somehow the picture was representing, to the best of our possibility, the quantitative version of the theorem. But then, fortunately, there was a team of Bortagaray, Lee, and Nocetto who decided to seriously use numerics to draw pictures of non-local minimal graphs. And this is actually a hard task because since the problem is non-local and it involves the whole space, and actually the stickiness is a long-range effect, one has to be very accurate in the numerics. And this is a picture coming from their paper. And so let me try to describe what happens. So in their case, n is equal to 2. So we are drawing here non-local minimal graphs in R3. The domain is this, well, the domain is a cylinder, right? But the cylinder is a small omega in R2 times R. The small omega is this L shape. And the datum outside is 0 in the vicinity of the L shape. And then there are some small bumps far away. And they wanted to see what is the shape of the corresponding solution. Okay, and the shape is something like this. But now it's very difficult to see what happens in this picture. So they decided to take sections of it. And the different sections showed different behaviors. Let me say that this is an interesting cultural difference between us and people working in numerics. Right? For us, the simplest possibility was to consider a smooth domain and then do calculations with that. But if you do numerics, well, squares and corners are the natural thing to look at, right? But that was a fortunate coincidence because the diverse perspective showcased also a different phenomenon in principle. So let me see. So for instance, this picture here comes, I think, from the diagonal section from this vertex to this other vertex, so the longest possible diagonal. What it seems from the picture is that at these two corners, you don't have stickiness. This looks like a continuous function to me. But at this vertex, you do have stickiness because the value here is, I think that they put the bump downstairs instead of up. So here the jump is from 0 to a negative value. Okay, so stickiness seems to occur at this point, at the center of the picture, but not at these two extremal points. This one, I think, is the section along one of the short sides of the L shape. Okay, And again, I think so. For instance, I think it's from this point to the opposite. And they were having stickiness, I think, here, but not here. And yes, this is instead the section on the long side, so say from here to here, and you have stickiness from both sides. If you see, it's kind of smallish, but it's a vertical segment here. And this, I think, is from here to here, so you have stickiness from both sides. But then it's curious in the sense that stickiness seems to be affected by corners and seems to be affected by different type of corners. So they pose a conjecture in their paper. They say, we see that the largest stickiness takes place at the reentrant corner, while there is no stickiness at the convex corners. This supports the conjecture that the minimizers are not sticky at convex corners. And then with Serena and Ovidio, we tried to prove this. And in fact, the conjecture is true. The conjecture is true, and it's actually even more general. So the difference is between pointing in and out, and it's more general in the sense that it's not only for corners. So for me, a corner is a singularity, but could be a cusp, or could be something that is differentiable, but not differentiable enough. So for instance, an outward pointing singularity is something of this shape. So locally, it is a graph of the function phi, but phi is not like quadratic, it's like the absolute, the norm of x prime to a power beta. And so beta equal to 1 would correspond to a corner. Beta smaller than 1 would correspond to a cusp. Beta larger than 1 says that you don't have you are still differentiable, but you are singular with respect to the scale of the problem. So the singularity occurs for me when beta is less than s plus 1, which is somehow the order of the operator acting at the corner. Okay, so basically you can think that you may even have a C1 plus alpha domain, but alpha is less than S. The inward pointwise singularity is instead something of this sort. The important part for me is that you are touched from inside by a set of class C1 alpha with alpha larger than S. And the theorems that we have go as follows. So first of all, for outward singularities, so for corners going out, for instance, in particular for corners going out, you have that S minimal graphs are continuous at those points. Of course, at other points at the boundary, they may well be discontinuous, so the continuity and the stickiness depends on the point you are looking at. If you have a complex domain, there might be singularities pointing outwards, singularity pointing inwards, or smooth points, and then you have different situations. But at singularity pointing outward, you are always continuous. And so the Bortagalli-Nocetto conjecture holds true in particular convex corners of two-dimensional domains. Yeah, so here I was trying to show the situation, right? You have a bump, so your non-local minimal graph will tend to go up. At smooth points, you have stickiness. So my domain is this, and the gray part is the non-local minimal graph. At smooth points of the boundary, you have stickiness, in general at least, but at this point here, in which you have like an outward singularity, you are continuous. The inward singularities are actually discontinuous. Stickiness occurs at inward singularities. Okay, this is maybe less surprising in a sense that you may think that if I have an inward singularity, I have a lot of space in the domain. So since I'm able to create stickiness for smooth domains, here I have even the possibility of enlarging the domain, so I shouldn't lose the stickiness, at least heuristically, but well, you have to prove it in a sense. And so this is the picture in this case. So now I have an inward singularity, and what I'm trying to say here is that the inward singularity has a nice domain, a C1 alpha domain with alpha larger than S touching from inside. And what I will do, I will create a sticky non-local minimal graph in the inner domain that will be used as a barrier for the full domain. And then this is basically, roughly speaking, the reason for which I have these vertical discontinuities at this point. So maybe I can say some words about the proof. First of all, the case of outward singularities. The case of outward singularities is based on a careful calculation of the non-local mean curvature. Yes, the idea is that I look at the non-local mean curvature equation, well, it's true that at the boundary point, I'm not really allowed to write the equation with inequality. But if I'm careful enough and I take the appropriate limit, I still have an inequality at these boundary points. And I can determine the sign of the inequality. So this is basically the first step, reducing the Euler-Lagrange equation to a boundary inequality in a limit sense. And then we argue by contradiction. So suppose that you have a discontinuity, then you have a sequence of points that I call pk, with the last component remaining, for instance, bounded away from zero, from the positive side. Okay. Now, the first observation is that this vertical value here is bounded. If it's a minimizer, at least roughly speaking, there is no need to waste energy at infinity. You have to check this, but I would say it's kind of intuitive that if the surface drifts too much on the vertical side, you can reduce its energy by reducing its height. So up to a subsequence, and thinking that the origin is the boundary point under consideration, we may think that this pk converges to the origin in Rn and to some positive value Pn plus 1 in the last coordinate. And then you have to investigate integral contributions. So here, basically what I'm saying is that I take a small cylinder centered at this point. Here the picture would be that I have. This is my domain little omega. Then this is the origin. Then the point pk is converging to this point here, big P. and then I'm looking at small cylinders around this point. So I have a small parameter mu. Mu is both the radius of this ball and this height, and this is what I call K mu. And the idea is that I have to check the integral contributions in K mu, and well, the integral contributions in K mu can be split. A bit difficult to draw it, right? But this is a cylinder, right? So the cylinder omega intersects the cylinder K mu. What happens is that outside the domain omega, the cylinder K mu doesn't see E because my datum outside is flat here. So here I can do the computation explicitly and replace it in the full inequality. So the inequality is in the full space. I distinguish whether or not I'm in the cylinder K mu. So the two contributions are the ones in K mu. The third contribution is outside K mu. In K mu, I distinguish whether or not I'm in the domain omega, where I know what happens because I don't have the set outside omega in K mu. So the first contribution is actually 1 here. The two other contributions I don't know, but the worst case scenario is that I put -1. Then I look at the last term. The last term is the complement of a cylinder by scaling is like mu to the -s. So this I know it very well. And then, so the annoying part is this contribution here, right? In the sense that I would like to say that these two parts mostly cancel out. And now, well, here I have phi. So the phi looks like a promising object for a cancellation, and they have opposite inequalities, right? So it's very tempting to reflect through the n direction, and then you change the inequality, the bigger sign to a less than sign. The drawback is that you also change the sign of phi, so you have to check the error that you have when you do this flip of signs. And well, again, this is sort of an explicit domain, and you can get an error like mu to the s. And then you perform this with the scaling. So you divide your cylinder in dyadic cylinders, and you perform this calculation, and you get a series of these contributions that look like this. And now you look at the numerology of these parameters here, and the kth summand is like mu to the beta -1 s, which is not infinitesimal when beta is sufficiently large, and then the series diverges. So you get the contradiction, and so you prove that your S-minimal graph was actually continuous at Albert. Well, the case of inverse singularities, you have to construct a barrier. I don't have time to go through that, but I think it's basically what I was trying to say in the first picture. So in principle, the first step is to take a bump out, to take a domain, a nice domain, C1 alpha with alpha larger than S touching from the inside, and you can put a Lipschitz function of this shape inside the domain. So this would say at least that you have some slope coming from the boundary, Well, when you have a slope, you perform a blow-up, you get a cone with a slope, but then you check that once you have a cone with a slope, the slope has to be exactly vertical, otherwise you violate the limit equation. And once it's exactly vertical, well, you have to use somehow, wouldn't say really an improvement of flatness, because maybe it's an improvement of verticality in a sense, but the idea is that you touch your limit cone with larger and larger balls, and you prove that the original set already had the vertical component. And with this, I think my time is over. Gianmaria was very strict, saying that I shouldn't go over midday.
Thank you very much.
Thank you.